We will continue the gas laws by talking about the ideal gas equation, which we will be using quite a bit. If all the gas laws that we talked about, so Boyle's, Charles's, Avogadro's law, if we combine all of those together, then we get the ideal gas equation. In class, I actually have derived this for my students before. It is not necessary that you know how to derive it, but this is know that we can combine all the previous gas laws into one called the ideal gas equation. This is now where all the everything is changing. So pressure can change, volume, number of moles, and temperature. Okay. P is pressure, and we use it depending on what the ideal gas constant is going to be, what the value is. You can have that expressed in atmosphere or millimeters of mercury, but typically the pressure is expressed in atmosphere. V is the volume in liters, not milliliters, but liters. N is the number of moles. T, of course, is the absolute temperature in Kelvin. And R is the ideal gas constant. Note that in this form, so 0.0821 is the value for the ideal gas constant if the pressure is expressed in atmosphere. If it is expressed in millimeters of mercury, it's a different value, so not 0.0821. However, this will be given to you, or you can just have it handy to actually do these types of problems. Even if it is not necessarily given to you expressly in the problem, you know that this is a constant, so just have it handy to use in problems. Here's a sample problem, and I've picked different ones here, each calculating one variable. So I have 1 mole of ideal gas at room temperature and 1 atmosphere pressure. What is the volume? Okay, note that you will use the value for R that is in the previous slide, convert the temperature to Kelvin first, and then use PV equals nRT to calculate the volume. The next sample problem asks you to calculate the pressure using the same ideal gas equation. So P times V equals N times R times T. In this case, we have 1.44 moles given to us. We have the volume, 5-liter container at 36 degrees Celsius. So make sure you convert the temperature to Kelvin first. Set up P times V equals N times R times T, and then solve for the pressure. This next sample problem asks you to calculate the number of moles of the ideal gas that has a volume of 12.3 liters at 298 Kelvin and 1.8 atmosphere. This is my mistake. You don't need to convert the temperature to Kelvin first because it is given to you in Kelvin. Use the same setup. So P times V equals N times R times T. Substituting, so plugging in these values for volume, for temperature and pressure, and the R that is already given to you as a constant. And lastly, what would the temperature be in Kelvin when you have 2.71 moles of an ideal gas that occupies 30 liters, that's your volume, at standard pressure, which is 1 atmosphere. So 1 atmosphere pressure, 30 liters volume, 2.71 moles, and R is 0.0821 liter atmosphere per Kelvin mole. Figure out what the temperature is by using the ideal gas equation, P times V equals N times R times T. Now, we can use the combined gas equation or the combined gas law, which contains three variables, and it's useful to us if we know two out of the three and we wish to calculate the third. So these are my initial conditions. These are my final conditions. So initially, if I have a pressure and a volume and a temperature, and I change two of the variables, what would the third one be, right? So I have P1 times V1 divided by T1. It will be equal to P2 times V2 over T2. Note that this really is a combination of Boyle's and Charles's law, right? So P1 V1, the top part gives me over or equal to P2 V2 at constant temperature, right? This falls out, the temperature falls out, and I have Boyle's law. At constant pressure, right, my pressure here would fall out because it would be constant, it would be the same number, and then I would get V1 over T1 is V2 over T2, which would be Charles's law. But this is called the combined gas equation, and I have three variables. I change two, and I need to calculate the third one, the change in the third variable. Here is a sample problem. So if I have a child that releases 6.25 liters of, so this is a helium balloon that has this volume, where the temperature is 28 degrees C and the air pressure is 757.2 millimeters of mercury, what will the volume of the balloon be when it has risen enough that where the altitude, to an altitude where the temperature is now minus 34 degrees Celsius and 366.4 millimeters of mercury? Okay, so what are your initial conditions? This is very important. This is your volume, temperature, and pressure initially. What did you change? You changed the temperature and the pressure. Calculate the volume, V2, so you're after V2. Convert the temperatures to Kelvin. Convert the pressures to atmosphere using previously, we've already talked about the relationships that have been given to you in tables in a previous video. So use those to convert the pressure units to atmosphere, and then use these to convert to Kelvin by adding 273. We will continue our discussion by talking about the molar mass equation. We use this equation when we have determined the density of a gas experimentally, and we want to determine its molar mass. So this is the formula. The M stands for molar mass. It's equal to the density D times R times T over P. Note that this part doesn't change, right? From the ideal gas equation, we have RT and we have a P. What are changing is the molar mass and the density. Now we can derive this, but once again, I don't think it's necessary for you to know it or remember it. So just use this form of the molar mass gas equation. So if you know the density of your gas at a certain temperature and a certain pressure, you know what R is because that is the gas constant and it's given to you. It never changes because it's a constant. Then we can calculate the molar mass of the gas at that particular temperature and pressure. And remember that it will be in units of grams per mole because that's the molar mass of a gas. Here is a sample problem for you to try using the molar mass gas equation. So if I have CO2, which is effective in fire extinguishers because it's got a higher density than air, so it can smother flames by replacing oxygen, right? Flames need oxygen to continue, but if I smother them with CO2, then it will stop. So air has a density of 1.2 gram per liter at room temperature and 1 atmosphere. Calculate the density of CO2 at room temperature, which is 25 degrees Celsius and 1 atmosphere. Okay, convert to Kelvin first. In this problem, you're actually calculating the density and not the molar mass. What you need to do then is calculate the molar mass of CO2 first. That will be your big M. And then that's equal to density times R, which is 0.0821, times the temperature, convert that to Kelvin, divided by 1 atmosphere, which is your pressure, and then calculate the density.